Well, it's really a pleasure to be here with you tonight and to share some of the things that I and others who have been presented with the wonderful opportunities to work alongside the Mars 2020 mission. We're seeking to better understand the origin of life in our solar system, and I come to this as an organic geochemist by training. My background is in the geological and biological sciences, and I first was working on trying to understand celestial mechanics. So this is the interplanetary dance whereby the axial tilt, the orbital configuration, and the wobble of the various planets result in gravitational pulls and tugs on the other planets and their moons. And this controls climate on really long time scales, which influences the ability to hold water and habitability. So I was very interested about this on our planet, and this created a nice backdrop to understanding these natural cycles. So I just realized that my video was off. These natural cycles of orbital forcing and climate changes and how that plays out into the stratigraphic architecture, that is the rocks on Earth, how that then filters out the type of life that can exist. And to contrast those background natural variability with episodes of abrupt change like mass extinction events where upwards of 90% of all species on the planet can be wiped out by singular events like planetary scale volcanic eruptions or by wayward asteroids, meteorites, cometary impacts that hit our Earth and have cascading effects, which gets into the limits of habitability here on Earth. So as you can see, it comes from a multi-dimensional scale of the big story of celestial mechanical scale of orbital configuration to the scale of how climate cycles work on various planets, to the scale of how biogeochemical cycles work, and therefore what life can get through mass extinction events and what life can't. And then also what this might mean for life favoring conditions elsewhere. For example, that little red planet. So that's how I'm coming to this, is from that type of perspective. And what I'm going to talk to you about today are, again, we'll see a little bit of influence of how climate and how that relates back to the geometry of Earth's orbit, which influences Mars's ability to control its climate, as well as the other way around, and then get into the exciting news about the Mars 2020 mission and what that has to do with the limits of habitability and potential life elsewhere. So hopefully you can see.
If I stop sharing, then there you go.
Are we able to see my screen?
Yeah, perfect. Thank you.
Okay, so let me introduce you to Perseverance. This is NASA's Perseverance Mars rover, and it's taking a selfie here. This is from the cameras that are atop Sherlock. So this is Watson, the wide-angle topographic sensor for operations and engineering camera that's communicating. It's atop the scanning habitable environments and Raman and luminescence for organics and chemical instrument. So that's on Sherlock. So this is on the rover's long robotic arm taking a selfie of itself with the Ingenuity tech demo, which we'll see a little bit more about a little later on. And you can see the title of my talk is There Life on Mars? The Swiss Army Knife on Wheels. So we'll get into that. And this is a story that has three parts to it. The first is our fascination with Mars. So we're going to look from a multidimensional perspective. That is, we're going to look from an interplanetary perspective of why Mars is important and why it is, even though it looks like it would be absurd to think there's life, even I'm talking extant life, that may not actually be so absurd whatsoever, because it started off very similar to Earth. And we know that Earth's life evolved in extremely intense, absurd environments. And then we'll move on to part two, and you can see in the little animation here, again, that's a selfie video that's taken from Perseverance that's showing you the Ingenuity robocopter tech demo. It's unfolding like a calf would unfold from a cow giving birth, and it's stowed position in the belly underneath Perseverance after it was charged and sheltered for some 44 days and nights, signaling that we'll delve a bit deeper into the tools and the actual suite of kit that's aboard the Perseverance rover, the Swiss Army Knife on Wheels, our planetary ambassador that includes that rover as well as the sidekick Ingenuity. And the final part will be on evidence for life-favoring conditions on Mars, the evidence that exists for that, and is this actually life's other cradle? So I mentioned that we're going to start off with the big perspective here, and it gets down to our on and off again fascination with the planet Mars. So you see the suite of other bodies that are potentially life favoring, so that might harbor life as well. We have Venus with its CO2 atmosphere gone crazy. We have Earth, obviously. We have Mars with its very thin atmosphere. The moon of Saturn, Titan, that has hydrocarbon water, hydrocarbon lakes that are present that might also be life favoring. And then we have Pluto at the end. And it's interesting to think about life favoring conditions on all these planetary bodies because it helps us think about understanding climates throughout our solar system, how they evolve over time. And this is fundamental to understanding planetary evolution as a whole. And it's important to be able to constrain the climatological evolution because that provides boundaries for whether a planet could have been habitable. And we obviously have one great data point, a fascinating data point, but it's just one data point, and that's coming from our own planet. And we have a whole suite of very interesting questions about planetary evolution in general. So how do climates evolve on planetary bodies that don't have plate tectonics? What about planetary bodies that don't have large oceans? What if there's a thin atmosphere like Mars, a thick atmosphere like Venus or Titan for that matter? And how do climates evolve on planets that don't have very large moons to stabilize their climate? Each one of these planets or moons is its own natural experiment. There are slightly different initial boundary conditions, but by studying them, we can help determine what makes our own planet unique and also understand the limits of habitability throughout the entire solar system. That brings us to Mars. So actually, Mars looks red in its current state, but in some ways, it's actually much better suited for preserving life than Earth because it lacks deep burial and tectonics. There's no plate tectonics on Mars, and plate tectonics creates heat and alteration that destroys organic molecules. Mars doesn't suffer from this, so it actually is an ideal place to preserve life, to preserve ancient life. And Curiosity, another rover, has shown us that it's actually possible to get below that rusty soil that's all an effect of the Martian hematite stained dust. And there's actually gray rock underneath there that might harbor traces of past life, possibly even present life. So let's just delve a little bit into the history of Mars. Mars, like Earth, is 4.5 billion years old. And when the solar system settled to its current layout, it was formed when gravity pulled swirling gas and dust and then coalesced that into the fourth planet from the sun. It is about half the size of Earth, and it's a terrestrial planet, meaning that it has a central core, it has a rocky mantle, and a solid crust. And it started out very Earth-like with lots of water, and it evolved then to an ice and wind dominated planet. And we're going to get into why that happened. It lost its atmosphere. It lost its magnetic field. There's no magnetic field today, but there is hints that it had a magnetic field in the southern hemisphere because there are magnetic particles. There's highly magnetized there. And that indicates that there actually was a magnetic field 4 billion years ago. So even though it's only half the size of our planet, the amount of surface area is of potentially habitable areas, that is like the same surface area of the Earth's continents, are actually on Mars. So there's at least the same amount of potential habitable real estate there. In the current Mars world, it's wrapped in a very thin carbon dioxide rich atmosphere, and it doesn't seem that it could support life forms like those on Earth, at least on the surface, but we'll see what happens underneath the surface. There's methane gas that periodically burps up into the atmosphere. Again, it's a desiccated world, no magnetic fields there to actually protect any life that might be on the surface from cosmic radiation or from solar radiation. And the soil compounds are toxic. So they have some sulfidic particles that are in there that are hazardous to life as we know it. And all the water in the current world of Mars is locked into the planet's icy polar ice caps, and it's buried actually possibly in abundance beneath the Martian soil. So we mentioned it has this very thin atmosphere, and we'll see how that comes into play. The other thing about that thin atmosphere, though, it means that there's not a thermal insulating blanket. So temperature is not well regulated on Mars either, at least when you are at the surface to the atmosphere. So on Earth, it's much more homogenized because we have a thicker atmosphere. But on Mars, you could be standing at the equator and it could be springtime, 20 degrees Celsius at your feet, but at the height of your head, it could be actually something like 0 degrees. So there's a massive gradient that's there because there isn't anything that's actually insulating that atmosphere. And occasionally there are winds on Mars that are strong enough to create dust storms that cover upwards of half of the planet. So you can see a picture of one of these dust storms on the right-hand side. And this is critical because the winds on Mars that are driving these dust storms, they're strong. They're strong enough to, as we said, actually cover that dust storm over half the planet. But it acts just like liquid water does on Earth in terms of the weather. So that's important when we start thinking about how to model Mars. It's easier to model the climate on Mars because it lacks a large ocean, but Mars actually had an ocean in the past too. It may have been a very acidic ocean, but there's apparently evidence that it had a hemispheric ocean. There's a static topography, and there's a huge swath of data that's been returned from lots of projects that involve the satellites, so the orbiting spacecraft around Mars, as well as the landers and the rovers. And just to get a little bit into my initial interest and my current work on Mars was coming at it aimed at understanding the climate parameters for habitability. And what you're seeing here are bedrock topography, so surface topography with the lighter shades being higher relative to what's around it. And Earth is being shown on the right and Mars is being shown on the left. On the right-hand side, the picture here is showing you a digital elevation map, and you're looking at strata, so rocks that are tilted and they dip from right to left, and there are ridges that you can see that are coming up. Those are the harder rocks, and the fine ridges are where there are deep water lake units that are intersecting the surface, and that represents a time when the Earth's orbit was like an oval as it goes around the sun rather than a circle. And that's due to the gravitational interaction of dense planetary bodies like Jupiter and Venus, and how that pulls on the Earth, making the axial tilt wobble, and that has the greatest climate effect here on our planet. Now, it turns out that there's a cycle that's caused by the interaction of Mars and Earth, and that modulates the expression of the Jupiter-Venus cycle on Earth, and these affect Earth's shape, the eccentricity going from a circle to an oval as it goes around the sun over really long time scales. When we look at Mars, on the left-hand side, you can see how similar it actually looks to Earth. This is a high-resolution imaging experiment. This is known as HiRISE, and this image is taken from the Becquerel crater. So it's combined from taking two images from slightly different positions, and it combines them to make a 3D stereo image, so a photogrammetry, and it's showing you the wall of the Becquerel crater. It's 167-kilometer diameter, and there's topography here that's formed by wind eroding sediments of different hardness from a lake that was deposited in this crater. And again, you can see there are a bundling of ridges. So there are lines that are within lines that are with lines that form these bundles, and those are showing you these climate cycles that are present on both of them. So it turns out Mars and Earth both feel the same gravitational cycles, but the effects that we see in these instances were produced at different time slices. So the ones on Earth are from the Triassic period during the dawn of the age of dinosaurs, actually from the same strata as the one that's showing me there with dinosaur footprints, while the ones that are on Mars are formed during the Noachian period, 3.7 billion years ago. And that's when there was abundant water on Mars and life had just evolved on Earth and possibly also had evolved on Mars. Now, Mars's climate is actually all over the place because it doesn't have a large moon that stabilizes the climate, unlike our Earth. So our tilt, our obliquity, is actually only 2.4 degrees, whereas on Mars it can vary by 60 degrees. So it can actually flip itself almost all the way upside down over really long time periods. Because it only has these two tiny moons, Phoebus and Deimos, that were named for the ravens that accompany Mars on the ship, but actually it's kind of a little bit of a joke because they're really, really small. So Phoebus is actually only 27 kilometers across, and Deimos is even tinier, only 14 miles across. Not enough pull to keep that climate, to keep the tilt stabilized, so it varies and switches all over the place. And we can see this on the right-hand side. So this is showing you the current situation of Mars, an incident when if the axis tilts to high obliquity, so more tilt in the middle, and it points towards the sun, then ice becomes unstable at the high latitudes and can form at the low latitudes. And when there's a low axial tilt, less than what it is now, the opposite occurs. That is, you can start getting more ice sheets that are formed up in the polar regions. Over long time scales, this is actually a chaotic pattern, and there is evidence that there's actually ice that's formed on the equator in the past on Mars, which is something that my lab has been working on from spectral images from past orbiting missions, because if there ever were human occupation of Mars, then astronauts would be able to tap into that water source possibly in the equatorial regions if we knew exactly where that ice is. So it gets locked up in the soil on Mars's poles during times of low obliquity, but during times of high obliquity, the ice sublimates at the poles and gets deposited in the low latitudes, sometimes even actually at the equator. So let's meet that Swiss Army knife on wheels. Let's meet Perseverance. And if you haven't refreshed your memory, here's just a 3-minute video of the landing. So also an opportune time if you needed to grab a cup of tea. But let's just watch that real quick.
Fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Applicate indicates chute deployed.
The navigation has confirmed that the parachute has deployed, and we're seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converged. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LGS valid.
We have confirmation that the lander vision system has produced a valid solution in part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
Back shell set.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN 50 Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started. about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
Yep, so that's the kind of technological miracle that I guess we come to expect from NASA and that always feels so humbling. So let's get into the Mars 2020 mission. So Perseverance rover, it has several objectives. They are to look for signs of ancient life, and it will have an astrobiological main goal, which is to search for biosignatures. And this is the part that I'm most excited about because my lab is actively trying to develop biosignatures and test them as we canvass extreme environments here on Earth that might mimic those in the past depositional environments of Mars. So looking for past biosignatures, chemical traces, fingerprints of past life, and also present life that might be harbored underneath the soil. So not on the surface, but underneath the soil, underneath that regolith, there might actually be life, either extant, more likely ancient life. Also to collect and cache samples for a future return mission, which we'll talk about, and then to prepare for humans. So to test technologies that might help sustain human presence on Mars someday. And those are the technology demonstration aboard Perseverance, Moxie, and Ingenuity, that helicopter. And Mars is the Mars surface exploration roadmap has been navigated by a suite of other rovers, and you can see the broader family here. This is actually artwork that's etched onto a metal plate that's attached to the deck of Perseverance, and the image shows all the rovers that have driven on Mars. You can see that the rovers have gotten much larger in size. They've become more capable of exploring the challenging terrain, and they've been outfitted with much more equipment through time. And you can see here also that there's a suite of black space, and that's because the journey continues on, and there's already in the works another rover that will go out and fetch the samples left by Perseverance, and then possibly even you or your niece, nephew, child, grandchild, anyone in the future might be out there as well. And the road may have been paved away by these rovers, these geological avatars in the pipeline that are there to help pave the way for future human exploration. So on the left, this is Sojourner rover. This was 1997, the year I graduated from high school. It was the size of a microwave oven. And its big demonstration was that it showed a robot could rove on the red planet. It was followed by twin rovers, Spirit and Opportunity, in 2004. Each of these are the size of a golf cart. And they discovered evidence that the planet once hosted running water before it became its frozen desert state. There was then Curiosity in 2012. It discovered that its landing site at Gale Crater had a lake that was billions of years old and an environment that could have supported microbial life because it actually found organic molecules. And we have Perseverance 2021 and its sidekick Ingenuity. And Perseverance is taking that next step, seeking to answer that key question in astrobiology: are there potential signs of past or present microbial life, biosignatures? And then you can also see pictured here Ingenuity that has now demonstrated that flight on another planet is indeed possible. And this is the kit that is outfitted on the Swiss Army knife on wheels, because lucky for us, our planetary ambassador actually is an engineer, a geologist, a biologist, a chemist, all packaged into one 2-ton sized SUV-sized rover that is roving around the surface, again, looking for evidence of life and paving the way for human exploration. So it'll be there for 687 days. That's equivalent to 1 year on Mars. And it's outfitted to sustain those huge temperature swings that I talked about from the actual surface to just a little bit up into just standing up. But then also this has to withstand the fluctuating temperatures at night, which can actually drop to below 90 degrees. So it has to be engineered for massive fluctuations in temperature and to support all the equipment that's on board. And it travels at about 150 meters an hour. So that's about the 10th the speed of a turtle that's on the move. And that's because it has so much equipment that's on board and is actively making observations as it's going along. So let's just have a look at the various pieces that are on the rover. So this is RIMFAX subsurface radar. So this radar that has waves that can reach 30 feet deep and will reveal what's underneath the Martian surface. And it also is able to do 3D modeling. So it might be able to identify things like ice or water that it might come across. Then there are a suite of cameras and other imaging devices. So this is SuperCam. SuperCam also has lasers. They vaporize rocks, and that reflects information back about the composition and the chemical makeup of the rocks. You can see Mastcam Z here. It has zoomable panoramic cameras. There are 2 cameras there. And then there are also some nav cameras, and they allow the rover to be directed from Earth. That Mastcam Z also has stereoscopic imaging instrument, and it's multispectral, and it can assess the current atmospheric conditions, the astronomical conditions, and it can make observations of the clouds and the dust that rains out, the properties that are all very much part of the active weather on Mars. It can also look at things like dust and ice crystals or other types of aerosols, and also aeolian transport of materials. And you can see there's also a weather station, that's META, that's on board, and that provides updates on weather conditions. There's Sherlock and Pixel, and they are above a very heavy rotating turret that's on a flexible 2-meter long arm. Pixel is the instrument that can look for chemical traces of life in rocks, and Sherlock uses a laser scanner and also has a suite of cameras like Watson. That's how it was taking the selfies, and they can look at the composition of rocks and soils. That allows Perseverance to go along mapping organic matter, the chemical composition and texture of different rocks, and do this all together at higher detail that has ever been possible by any Martian rover in the past. And all of these instruments play an important role for assessing life, but particularly Sherlock and Pixel. And we also have here MOXIE. So NASA, again, is preparing to send humans to Mars, and MOXIE has successfully demonstrated that this might be possible because it can produce oxygen from the Martian-rich CO2 atmosphere, which allows for both a rocket propellant and for breathing. And here's MOXIE up close. So it converts CO2 from the Martian atmosphere into oxygen, just like a tree. So MOXIE breathes just like a tree. It makes oxygen like a tree does. It inhales that carbon dioxide and it exhales oxygen. It's the size of a car battery. And the future oxygen generators that NASA is looking at that would actually support human missions on Mars would be about 100 times larger here. But the important thing is that it's demonstrated just last week that you can make homemade liquid oxygen on Mars that could supply 3/4 of the propellant that humans would need for exploration of our friendly little red planet. And one of the tech demos, so this is Ingenuity, and here it is in one of its flights. It was the very first powered controlled flight outside of Earth, 117 years after the Wright brothers. It actually had a piece of the original plane aboard it. And it's had 4 successful flights as of the last day of April. It's now going into a higher risk demonstration stage where they're going to try to run it to its limits, even if that means sacrificing Ingenuity, because it is paving the way for the limits of what's possible in the future. There might be some of these that are actually outfitted with their own types of kit. Maybe there'll be some that have things like methane sniffers that can go around. There might be some that can go up into areas that actively have cascading water and look for life. I mean, there's all kinds of possibilities with Ingenuity setting the scene here and what that might mean. It was also another one of these technological miracles that we come to expect from NASA, something that conjures a lot of imagination because under the most absurd conditions, it was able to take off. In terms of atmospheric conditions, that's critical for lift because a helicopter or a or an airplane needs to bite into the atmosphere, and the atmosphere on Mars is 1% that of Earth. So to make up for that, it had to be a very light instrument. It's only 1.8 kilograms, likened to about the size of like a small cantaloupe or a chihuahua. And it looked a little actually like a child's toy. It actually has spindly looking legs that are kind of like a coat hanger, and it has foam blades that are covered in carbon. The rotors are spinning at 2,400 rotations per minute. That's in contrast to on Earth being 400 to 500 for a helicopter. And this had to survive the frigid temperatures during the Martian nights that can exceed 90 degrees Celsius. And it had custom components. I mean, it was just another one of these absurd feats that looked impossible, but nonetheless was not. So those are the tech demos, and now we move on to actually evidence for life-favoring conditions. And this is something that's been in humanity ever since, you know, ancient civilizations looking up into the night sky. Galileo, who first imaged Mars from a telescope 500 years ago. And the idea of life living on Mars was actually in the Victorian mindset. Even learned individuals believed that there were canals that were built by Martian aliens, thanks to Giovanni Schiaparelli. So we're looking at his maps, these 1888 maps, where he actually outlined where he thought there was water in blue, and gave everything like Mediterranean names. He renamed everything on Mars basically to say it's so different than everyone thinks that I actually had to come up with new names. And he did believe that these canals were created by aliens. 1907, that's one of the first images of Mars, and people did think those were canals, but we see that it's infiltrated into the literary realm as well. Lots of visions of Mars and extraterrestrial life. We have this 1898 example, War of the Worlds, where a witness recounts an epic battle between Martians and Earthlings in H.G. Wells' notorious thriller. We have Carl Sagan's vision for National Geographic in the middle. Carl Sagan was my former father-in-law when I was back in the United States, but he imagined radiation-resistant Martians that were shielded by glassy shells, and they would be eating cabbage-like plants that fold up at night. So there was a nocturnal component there based on the current conditions of Mars. And then 2015, there's this Andy Weir's futuristic survival novel turned movie that starred Matt Damon as an abandoned botanist who seeks out staying on the Martian surface. So what about life on Mars? So this brings us back to fundamental question: what are the ingredients of life? Well, you have to have chemical building blocks. These are carbon, oxygen, hydrogen, and nitrogen. They are in abundance in Mars. There needs to be an energy source, whether that's solar or chemical, also check for Mars. There needs to be evidence of liquid water, because that is the mantra of NASA, follow the water, and that there's habitability. Those are the conditions that are suitable for life. So that brings us to the question, well, what's actually the evidence for life on Mars? And we know that there's ample evidence of water, actually, since the Mariner orbiters went around. There was detection that there was liquid on Mars as far back as 1974. So we know this from the past, from orbiting spacecraft, as well as asteroids and meteorites. We know it from the present with our rovers, and possibly for the future again, about fantastic discoveries that might come from human exploration. So let's look at what this evidence is. We can see up on the right, that is early Mars, full of water, a blue planet. And it's showing you also the continents, again, the same a mass surface of continental space that the Earth actually has. And the evidence for that water comes up from the first picture we see. These are dried up riverbeds. So they're showing you evidence of ancient glacial events on the Martian surface. These are called oxbow bends, and they only occur in the final stages when there's a slowly flowing river. At the final stages of the life of that river, that's when those oxbow bends happen. And this one's found on Mars. And there are lots of channel-like features that originate from Martian glacial past. There's also lots of evidence that there's been a history of liquid water flowing on the surface, like in rivers like this dried up bed that we see here. In the bottom left, we see the so-called blueberries. So these are little hematite spheres, and they are imaged by the Mars exploration rover from this particular picture. They're almost certainly evidence of past life, liquid water on Mars, possibly evidence of past life. And then there's obviously lots of evidence that there's sedimentary rock. Sedimentary rock on Earth is only formed in aqueous environments. And we know from subsurface that there's ice, snow, and even frozen surface water on Earth in real time. On the right, we see something really cool. And this is an image that's taken from the high resolution imaging science experiment HiRISE camera. And this is something called recurring slope linea. So this is active cascading water striations that happen seasonally, and they're confirmed to be signs of salty water running on the surface of the planet. So briny water cascading down. These are areas that would be wonderful to go to look. Obviously, a rover wouldn't be able to get up into these sheer cliffs, but an Ingenuity-like helicopter of the future might be able to do that and take samples. That brings us to the next question. Well, what's the evidence for life? And there are really three pieces of information that we have, at least in terms of life, from what's been known to date. One is from the Viking 1 landers. These results show basically what they were doing is they were injecting a nutrient solution into soil samples from the Martian surface and looking for radioactivity, which they felt indicated metabolism. And so what you see in this figure on blue is a control sample and on red is an active sample. And you can see that the active sample in red looks like there's a jump in radioactivity, possibly indicating that there's metabolism, but there's a lot of conflict. There's a lot of debate about what these samples actually mean. But it was the first astrobiology experiment that was run by collecting the regolith, the rocky crust, and the soil, and by adding water and adding simple organics and seeing what happened in incubations. And you can see gases were actually released. So it's hard to know, but that's the results from Viking 1. Then we also have 20 years later, NASA announced that it found possible signs of life on Mars, and that was from a meteorite that was found in Allen Hills in Antarctica, forever known as ALH84001. And that was from imaging, which looked very similar to bacteria. And so it was thought that possibly that was evidence of life on Mars. That meteorite was dated to be 4 billion years old, so 4 billion years old on Mars, but then landed into our planet 13,000 years ago. And it had these magnetic particles that are known or expected to be produced by mostly biological processes, but could have some non-biological processes that could produce those crystals as well. So again, it's one of these potential signs of life, but it's not completely confirmed. And most people, I think, would say that the evidence doesn't support it in a demonstrable way. Then over the past 2 years, we have Curiosity, which maybe found methane vents, which is the picture on the right-hand side. So sample analysis on Mars, the SAM laboratory, which is the main chemistry lab that's aboard Curiosity, detected hydrocarbons. It also saw other organic molecules, and it showed that they had something really interesting, which was burps of methane that was being emitted from certain locations only seasonally and only at the end of Martian winters on the onset of spring. So that again is another one of these potential signs of life that can be produced mostly organically, so only by life, but there are ways to actually get an inorganic product that's making methane as well. So it's another one of these, it's again hard to know, but those are the lines of evidence for life at the moment. That brings us back to, so we have all the building blocks of life. We know that there was water on Mars. We know that there are organic carbon molecules from Curiosity. What in the world happened to make it appear to be a barren planet if it originally looked like this? So on the right, that's the original blue planet. And then on the left, that's a picture, an artist's depiction anyway, of the current situation that looks like a barren world. So what happened to all those enormous liquid bodies of surface that were lakes, that were rivers, that was half an ocean 3 billion years ago? What happened? And one piece of information that we know from this comes from the Mars atmosphere and volatile evolution. So this is MAVEN. This is an orbiter around Mars that studies the upper atmosphere, the ionosphere, and interactions with the sun and solar wind. Because the story of the loss of water is intricately related to the loss of the magnetic field And MAVEN has shown these magnetic particles in the southern hemisphere, indicating that it did have a magnetic field just like Earth. So this so-called dipole magnet, which is what's depicted on the right-hand side on the early Mars, but then it lost it and became what you see on the left-hand side, which is its current state, where it does not have a magnetic field. And because it doesn't have a magnetic field, it basically lost the water, possibly, or at least the atmosphere, was just basically blown off and lost to solar wind, destroyed by the strong solar wind, escaped to space. So it's basically death by magnetic field, death by loss of the dynamo. But that still gets back to, okay, so it's lost by the magnetic field, but then how exactly did it lose its water? And the first is atmospheric escape. So what I essentially just explained to you, that's the most popular hypothesis. That's been the conventional, traditional explanation, is that Mars's water just escaped to space through atmospheric escape. The planet lost the gases of the atmosphere, they got sucked away, and it just really disappeared into space. And the atmosphere then thinned out. And the water molecules, therefore, would be doing exactly that. Another option is that it didn't actually go up, but it actually went down, and all that water is actually present underground. And there's actually a new model just published a couple of months ago showing that 30 to 99% of the ancient global water is still found, but it's found in the Martian crust. So it's actually in the minerals that constitute the rocks, rather than being in the liquid form. So that's one possibility, is that it went underground. Another possibility is that those unwieldy dust storms, the dust devils, actually drove the water off. And there's some evidence from MAVEN, again, from that orbiter, showing that the surface has been slowly sucking away the planet's water over the course of millions of years, maybe sweeping water molecules off again on a wild journey into the atmosphere and then off into space by solar wind. And another option is that actually, if you were getting this on a multiple choice exam, you would just choose all the above. Maybe all these things happen, they just didn't happen at the same time. They're not mutually exclusive. So maybe one of these scenarios happened at one point, and then it switched, and a little bit of each of these is what happened to the water on Mars. But in any case, getting back to the hunt for life, Mars did have water. One place that it had lots of water was the Jezero crater, the landing site. Here's Jezero here. It's about the size of two Lake Windemere's. It's 3.6 billion years old. Again, another wayward rock fell in. An asteroid impact hit this, creating a crater, and then it filled with water, a large lake. It was fed by two rivers. You can see in blue, that's actually a delta. The interesting thing about this is, again, because there's not plate tectonics, that means that the sediments basically brought in by the rivers, captured, and then just deposited layer by layer like a cake, like a layer cake stratigraphy, and not altered, not heated up into high pressure and temperature like on Earth, subjecting it to the burning and destruction of organic molecules. So it's a great place to look for life, even though it looks like a dry desert today. And that presence of that delta implies deposition also of clays. We know on Earth that deltas have high organic preservation potential, and there are also lots of carbonates around that rim. That's confirmed by the orbiters, and we know that high carbon contents in the ancient lake water, and we know that from these carbonates on Earth, you know, like where coral reefs and that type of thing are, there's lots of life in those type of areas. So it's a great depositional environment. What are the central outstanding questions? Well, how was Mars wet? Was that water habitable? Was that water available consistently enough for life to actually originate and to subsist? And we therefore could see a record of that.
The planet Mars has been mysterious for centuries. But over the past few decades, a fleet of orbiting and landed spacecraft has greatly advanced our understanding of it. Based on this knowledge, Mars scientists are now ready to take the next big step, bringing Martian samples back to Earth, where the full power of our terrestrial laboratories could be applied to unlocking the story of the red planet's geology, climate, and especially its potential for life, either in the past or even today. But however you tackle it, returning samples from Mars is definitely a complicated problem. So how could...
Oops. I don't know what, I'm not sure what happened there, but this is just to show you how that sample return actually works.
Store them in sealed tubes for possible return to Earth. NASA and the European Space Agency are now working together to explore options for a pair of missions that could take the next steps to bring these samples back. In one scenario, after the Mars 2020 rover has placed its collected samples on the Martian surface, a second follow-on mission would land nearby, deploy a small rover to fetch the samples, and bring them back to the lander, where they would be loaded into a container and placed atop a small rocket. The rocket would then lift off, carrying the samples up into Mars orbit. Waiting in orbit would be a third spacecraft, an Earth return orbiter, that would find the samples in space, catch up with them, capture the container, and bring it back to Earth. With Mars samples safely back on Earth, scientists around the world would be able to study them in state-of-the-art laboratories for decades to come. The payoff of a sample return would be a breakthrough in our understanding of the history of Mars and of the potential for life beyond our home planet.
Okay, so that's the story of is there life on Mars, and that's that next great technological miracle partnership of European Space Agency and NASA, the interplanetary relay race or Easter egg hunt to pick up the samples that are being collected by Perseverance by that sample fetch rover, bring it to the ascent vehicle with another rocket coming back into the Earth's atmosphere and depositing those samples, which basically accumulate to the size of just a loaf of bread into the desert in Utah, and then are fetched out to various laboratories. Very excitingly, our lab, it will be one of those looking for biosignatures of those samples. And I'm happy to entertain any questions. Thank you.
Jessica, do you know when you get the impression that your job's really inadequate? You know, and you're sitting there looking at everyone, what you guys are doing. It's just bonkers, isn't it? It's great. I mean, just absolutely fantastic. Look, that was brilliant. I've got a few questions, but I'm not going to monopolize it like I normally do. There's a couple in the chat. So I'll read those out first, and then, or Jeff, if you want to come off mute, do you want to ask a couple of the questions that you had?
Yeah, okay, fine. Thanks, Phil. Jessica, two questions really. I mean, one, I think fairly early on you mentioned natural cycles of climate change for planets.
Mm-hmm.
And really I was wondering for Earth, how does this natural cycle interact with man-made climate change? Are they, I guess, at two extremes? One end is that they're mutually reinforcing, which could be bad news, or there might be some offset in terms of man-made climate change and natural evolution of climate change, planet climate change.
Yep, so that's a great question. And it's one that's actually brought up many times by climate skeptics, that there's massive variation on Earth's climate. So our current values of carbon dioxide in the atmosphere are 420 ppm. We know from Earth's past that values have actually been up to 6,000 ppm. Now that also has to do with a lot of things, that a lot of different boundary conditions. One is that our sun started out much less luminous. So it wasn't as bright.
Mm-hmm.
So over time, the sun has become brighter and brighter. And at the period of that atmospheric CO2 was 6,000 ppm, happened to be at a time where there was more, so it depends on the sun's luminosity, basically. So there had to be higher greenhouse gases for life to subsist on our planet, and it's been a steady evolution. Now, the cycles that I'm talking about are the ones that actually have been shown to pace or to control the most recent ice ages. So the Laurentide ice sheet that waxed and waned, that's all controlled by parameters of Earth's axis, its axial tilt, so that obliquity that controls seasonality, and the wobble. So it turns out our Earth is not a perfect sphere. It's actually pear-shaped, and it wobbles and it tilts, and then its orbit goes from being a circle to an oval. And all of those interact with each other to create worlds of, I showed you what happens with high obliquity and low obliquity. That's on Mars, where there's a variation of 60 degrees. On Earth, it appears to be less subtle changes, but with high impact to those subtle changes, because it's about the distribution of energy over our planet. So, and it sounds like that wouldn't be enough, but it's enough to change CO2 in the atmosphere from 150 ppm during interglacials to 300 ppm out of interglacials, right? But now that's the natural variation, 150 to 300. But then we have the human condition adding that extra 120 ppm. So you may have heard someone bring up something like, well, the natural variation dictates that we should be heading into a glacial interval. And that's true. We should actually be getting colder, but we're obviously not. So the natural cycles have been broken by anthropogenic climate change. But it is true that in Earth's past, there have been wild variations, and these very wild variations are controlled by, on the very long time scales, the Earth's orbital parameters. And then very, very interesting, the other planets actually on even longer time scales control the very long-term evolution of climate on our planet. So even Jupiter and Venus particularly, because they're the densest planets in the solar system, their gravitational pull creates really long-term cycles on the 405,000 year time scales. The cycles that I've been talking about, the shorter ones, are on the 20,000, the 40,000, the 100,000 year time cycles. And they all get their names from a Serbian meteorologist, Milutin Milinkovic, who actually figured this out by pen that he smuggled in during a prison sentence in World War I, because he happened to take his honeymoon a couple of months too late. And one of his fellow Serbians executed the heir to the Austro-Hungarian Empire, causing World War I. And so Milinkovic, unwittingly, going on his honeymoon to his hometown, was taken and actually sentenced to prison, and sat there and said he'd never felt so more alone, but felt like he was in a cell that afforded him the ability to solve this riddle of what caused the ice ages. And as soon as he was released, wrote one of his key papers that was on the climate evolution of Mars.
Well,
stay tuned, because I'm actually writing a book on this. It's fascinating.
Can I ask my second question, Phil? Is that okay?
Yeah.
Everybody's thinking of theirs. I mean, the other thing that occurs to me is that, I mean, our whole approach seems to be, and I understand why it would be, that we look at life as we know it. We then sort of back out from that what the building blocks are, which has actually created that life. And then we're out there searching for those building blocks to think if life as we know it could potentially be out there or could be recreated. But is there a possibility that there's another parallel path where there's some other form of life which isn't built upon any of the building blocks that we know? Is anybody thinking about that, or is there any interest in that?
There is a great deal of interest in that, and there are big NASA initiatives, NASA and I should say European Space Agency and initiatives. There are huge astrobiology centers. I'm part of one called the Alternate Earths, which is trying to think about other chemical pathways that don't involve a carbon-based life, which is the life that we know it, the hydrocarbon-based one. So it's possible that there are other avenues. It's just it means trying to. I mean, the other thing is it breaks down to the building blocks to something called chirality, which gets down to like the fundamental atomic structure that allows then for cells to build. But again, this is all from the perspective of what happened on Earth.
Yeah.
Some of the ideas, even for our own planet, we don't know if life actually evolved multiple times, and the lineage that we see is the one that survived. There could have been lots of failed experiments at creating life, and it was short-lived, and we'll never know if there was another pathway that just wasn't successful. But we do know that Mars and Earth, the reason why we're still coming at it mostly from what we know is because, well, that's the easiest for us to test, but also because Mars and Earth were created they formed at the same time. And they look very similar from what we can tell, at least in their very early history. So it's possible that there was actually even shared, they may have even shared some of the water. Because we know that asteroids hit other planets. So we've been bombarded by meteorites from Mars, pieces of Mars that have broken off and hit our planet, like the one in Antarctica. But we have hundreds of samples of Martian material. So likewise, there could have been Earth ones that were going. So there could be that the planets dually interceded each other. That is one active line of research, but you're right that it would be great if we had unlimited resources and could test everything that anyone could possibly think of to see if that would spark life.
Thank you.
Maybe you should join one of the astrobiology centers.
Yeah, thanks, Jeff. A slightly less intelligent question from me, if that's all right. I'm just wondering why Southampton is sort of involved in this. Does it have special skills or experience in this area? Just trying to sort of associate what you're doing with the local region and how it sort of came about.
Okay, so I'm interested in this. Like, basically, there was an open call for anyone who's interested in Mars sample return. There's an open call to write proposals and to basically make your argument of what you would do with the samples. And so what we've been doing is, for the last couple of years, we've been canvassing other areas or lots of areas on Earth that are potential analogs to Jezero and to some of the other exciting areas on Mars that samples might come from. So there are impact craters that have similar infillings to Jezero. That is, they have some of these carbonates that are forming in alkaline conditions. And one of these is the Reese crater that's in Bavaria. So this is a Miocene age lake, but we've been doing a lot of work of testing some of these biosignatures. So looking at nitrogen proxies, which can give you information about certain types of bacteria and also salinity indications. And then working on my specialty in organic geochemistry is working up basically fingerprints or molecular fossils here on life of microbial metabolisms that exist through mass extinction events when things like the seas turn completely sulfidic. So hydrogen sulfide that exists in mid-ocean ridges that naturally exists on the surface of the seafloor actually rises up into the water and goes up, killing everything in its wake, and possibly the entire oceans were sulfidic. So to understand that, you have to start thinking about testing for other kinds of signatures, right? So it was microbial ones. So it's building up the repertoire of microbial fingerprints that we can look at here on Earth. And then also there are other proxies like boron, which tell you carbon dioxide of the setting. And one of the leaders in the boron proxy is at Southampton as well. So
okay. Brilliant. So
yeah,
we've got
really
sort of world-leading testing capability around that sort of stuff. Okay, that's interesting. I'm aware. Does anyone else have any questions? Mike Palmer, you've just raised a question. Do you want to come off mute and ask me? Mike, are you there? I'll read this question out if we can't raise him. So Perseverance can't drill down very far, 5 centimeters. How useful would we have samples from deeper? Thought it might visit the Sky Crane crash site to see what was thrown up, but that's not the plan. Mike, sorry, are you able to speak now?
I think so, yeah. If you've read the question, yeah.
Sorry, stole your thunder. Apologies for that. Jessica, did that make sense?
So I heard the first question was, why is it only a 5 centimeter drill or a drill plug? And that's a great, so obviously it would be nice to have much deeper, but because it's always a balance of the payload weight and the limits of what has been tested on Earth in order to get repeatable samples. So yeah, you basically, each sample is just going to be the size of a piece of chalk. But the reason that we think that still will tell us about life is because of our experience on Earth, but also because the Curiosity rover had a drill, but it was only getting just below the subsurface, which is why we know underneath that red regolith, there's actually gray rock, non-buried gray rock. And we know on Earth in some of these areas that are super weathered, that are analogs, the terrestrial analogs, like I was mentioning, that we've been working on, we know that right below that weathered surface that looks red and like, it's actually called popcorn because it looks like popcorn, it's all cracked. Underneath that is material that we can extract biosignatures from. So the hope is that if even if you have 5 centimeters, that is deep enough to look for evidence of life and to look for other other information like the amount of water that's stored in basaltic rocks. There are all kinds of information. There are also people who will be dating the various rocks that come back so that we know a little bit more about if there is life in any particular interval, we'll know how old that rock is. So yeah, eventually it would be really nice if there could be longer cores that are taken, but it's all a cost benefit analysis about just what, to begin with, what Perseverance can actually promise and then deliver upon, but then also thinking about this is just, Perseverance is one in a trilogy of Mars sample return. So there still has to be the fetch rover that can go and pick up all the samples and then put them delivered safely into the Mars ascent vehicle, where it's basically needing to deliver something the size of a loaf of bread into something that's the size of a football or a basketball, really. So all of these had to come into play when determining the size of the actual core that can be taken.
Mike, did that answer your question, mate?
Yeah, well, there was a second bit which I understand that the Sky Crane and the Aeroshell both crashed into the surface. I wondered whether they'd visit that to see whether that had thrown up anything interesting from below, but the plan, I think, isn't to do that.
Yeah, that's a great question. And I think there was some discussion about whether the rover should stay there and try to do anything with that, but then they decided to go ahead and go on so that they could test ingenuity, because they were trying to bracket the time that there could be influence of some of these dust storms on Mars that would make ingenuity a no-go. So I think it's all about the planning. And I once was talking to Katie Sullivan. This is the director of NOAA in the US, but was the first American woman to walk in space and the person that actually put the Hubble telescope up. And she told me that basically they're all trained in the everything's the plans are always changing. So who knows, they might go back and look at that because it's a great idea, but it's always there's never one plan. It's the planning process of A, B, C, D, E, F, G, H, I, J, and then it's always what makes sense to do when the decision comes. If that's a great point.
Thanks.
It's so complicated, isn't it? I mean, the whole process is mental. I mean, that whole thing. So just so I'm clear, so the Mars samples are going to be the size of a loaf of bread. That's the total amount.
The total amount of all 41. Yeah.
Crikey. And yeah, the process of getting that off another planet into another spaceship, back into our world, it not crashing into the sea. I mean, there's so many things that could go wrong there. It's insane. Michael, you have a question, sir?
Yeah, and linked to that, it was just roughly if everything were to go well and making best assumptions and all the rest of it, when might those samples get back to your lab, Jessica? I mean, is it going to be? It's unlikely to be next weekend, but it might be in a few years' time, or is it 10 years' time? What kind of rough time frame are we talking about there?
Yeah, so it is 10 years. So the current plan is that in the 2026 to 2027 time frame, that would be the launch of the Fetch rover and the rocket that would go out with it, right? So then, I mean, as we've been talking about, it's the amazing technological advances that NASA pulls off. But this would be the first time that a rocket actually launches from Mars back to Earth. But the idea would be that the samples would be dispersed as early as 2030, possibly 2031. So yeah, it's 10 years.
Cool. Crikey. Does anyone have any other questions for Jessica? I appreciate we're a little bit over on time. I'm surprised Chris Cooper or Alex Reardon haven't chipped in yet, because they normally ask some quite big questions. Alex, Chris, got anything? Silence is not how they normally operate.
Right, since you're asking, Phil, since you're asking, Jessica, that was absolutely fantastic, by the way. Really enjoyed that, although it went much over my head. When these missions are being planned, presumably you look at the technology available and you've got to make a decision between deploying that technology that you know is reliable and actually going for something that's a little bit better, but not quite as reliable. What sort of decision processes or trade-offs get made? And do you sort of get frustrated that you can't actually be quite as cutting edge, and boy, oh boy, what you're doing is cutting edge, but can't be quite as cutting edge as you would have liked?
So that's a great question. And I think Perseverance is a great example of this, because what was done with Perseverance is learning from the trials and tribulations of curiosity and the things that people wish curiosity would have been able to do, and the foresight of people of trying to get those. So what happened with Perseverance is that there was kind of tried and true tested methodology or instruments, but then were outfitted to be even more precise with cutting edge technology. But then there were 2 tech demos that, you know, Ingenuity, which even when the planning was first, when someone mentioned it 10 years ago, all the engineers that ended up being the lead engineers on it said, that's impossible. You can't get lift on Mars with that atmosphere. We don't have anything that could fly so light. And even with the less gravity, it's not enough to counteract. But they went ahead and tried it anyway. And it turned out that the technology was advancing. So that really was like a last minute decision to put Ingenuity in. And then the same thing with Moxie was another one where it really was like people flying by the seat of their pants. Well, let's just try it and see. But yeah, there are always trade-offs, and
I mean, fun, but they are bleeding edge. Brilliant.
Yeah, that whole generating oxygen on Mars is, you know, from this really small Moxie thing. So how big could that scale up? How does that mechanically work?
Yeah, so the idea is that they would scale that up 100-fold.
Right.
And so there would be actually small centers that would be deployed eventually. Mm-hmm.
Wow. And then I suppose that gives you a critical mass to sort of sustain a small amount of life. And would the plan then be, on this is a really schoolboy question, so I apologize, but would the plan then be, could you start planting trees, or, you know, creating life that would then sustain it on a more organic basis?
I think there were people working on all different kinds of aspects. And, you know, before I was at Southampton, I was at Brown University, which has a great planetary geology program. And some of the students that I sat on their committees, many of them are actually working for all kinds of startup firms that are working on what's going to be on Mars, how to make clothing from the basaltic material there, how to grow watercress on that type of regolith. So there are actually people who were already working on all sorts of aspects of possible agriculture and greenhouses on Mars and how that might work.
My God, that's a job and a half, isn't it? I do boring procurement contracts for a living. Has anyone else got any other questions? I'm just aware that we're all overrunning a little bit.
Yeah, hi Phil. You tempted me. So Jessica, thank you. That was awesome. Just one very quickly. We saw that the Falcon rocket went up and down as successfully. And when do you think we will have? I know you said it could be our children, our nieces, our nephews, but go on, give us a punt that we can finish on and say it will be in the year 20 or 21 that we could be there somewhere.
I really think in the next 15 years, there will be human exploration of Mars. Mm-hmm.
Wow.
And if Matt Damon is the first on the I would strongly suggest we don't go. Thank you very much. That was awesome learning. And my brain hurts. I love it.
Any last minute questions, anybody, before we call it to a close? Brilliant. Well, look, I mean, Jessica, again, thank you. It really opens your eyes to what's going on in the world outside of our mundane lives. So yeah, really appreciate that. Yeah, round of applause from Jeff. So yeah, I'll be recording this, so I'll give you a shout afterwards, Jessica, just to confirm it's okay to publish it, if that's all right. We'll talk about that later. But on behalf of everyone, I really appreciate it. And thank you to all of you who did get through the complexity of the links that we had. We'll sort that problem out for our next webinar. But yeah, really appreciate it. Thank you very much, everybody.
Oh, thank you so much for having me.
Cheers, Jessica. Thanks ever so much.
Thanks, everyone. Bye.
Cheers, guys.
Thank you. Bye.
Got to try and work out how to stop recording now.